Thank you very much, everybody. So I will talk about our project on next nanosystems for abundant data computing. As you can guess, most of the work has been done by my students and my collaborators. I just have the honor to be here to give this talk. So I would like to acknowledge them first. So the whole purpose of this presentation is to see how we can improve computing performance, which means that we have to first define what performance is. And for the purpose of this presentation, we focus on what I call energy times execution time. That's because there are many ways to improve energy at the cost of execution time. There are many ways to improve execution time at the cost of energy, but there are very few ways of improving energy and execution time simultaneously. And you could think about maybe using device approaches or design approaches to improve computing performance. We'll come back to that. But before that, let's look at what are we running up against. So if you look at these abundant data applications, for example, AI would be an example of that. The single most challenge in these abundant data applications from the edge all the way to the cloud is the challenge of the memory wall. If you look at that pie chart over here, I did not write whether it's energy or throughput, because it doesn't matter. 95% is spent in trying to access the memory. And many people directly connect this to von Neumann and non-von Neumann. The point is, even if you had a non-von Neumann machine, for example, a hardware accelerator, you are stuck with this memory wall. So even if you had a non-von Neumann architecture, you have to worry about this memory wall. So both processors and accelerators have this challenge. And if you look at brain-inspired computing models beyond traditional neural nets, for example, Tana is going to talk about hyperdimensional, for example. It's the same challenge. You have to worry about compute and memory. You have to worry about dense connectivity. You have to worry about energy efficiency and so on. And if you thought that this was a big problem, this is only one of the problems, because we already have the power wall. All of you know about that because Dennard scaling has stopped more than a decade now. And moving forward, nobody really talks about this. We have the miniaturization wall. That's shown by those Russian dolls over there. And I actually made the font sizes in such a way that you can see that going from 5 nanometer, how far are you going to go? To 0.5. And oh, by the way, there are many other walls simultaneously. For example, the interconnect wall, cooling wall, and so on and so forth. So the real question is, given all these walls that we are facing, and given that at this same moment in time, when the world is requiring the best performance that they can out of us, how do we do that? How do we achieve 1000x improvement in performance that I was talking about? And just device level approaches, or just design level approaches are not going to cut it. We need something that combines device level techniques with design level techniques that clearly requires new innovations. And there comes this notion of what I call nanosystems. So what are nanosystems? You start with nanotechnology, for example, nano devices, new ways of fabrication. I will talk about one today, new kinds of sensors. Now, you have to worry about imperfections. You have to worry about large scale fabrication. You have to worry about variability. You have to address all these challenges in the context of nanotechnologies, because on one end of the spectrum, you're talking about things really small. I'll talk about stuff that's at 1 nanometer scale. And on the other end of the spectrum, you're talking about hundreds of billions of those really small things. So you actually have to overcome these challenges. And when you do, now I want you to remember this one. It's extremely important that you enable a new architecture that is not possible with existing technologies. Because if we just go and replace our existing transistors and memories with new transistors and memories and do not change the architecture, then the bottlenecks of our existing architectures will continue to stay. So it is very important that new nanotechnologies enable new architectures that are very difficult or almost impossible with existing technologies, for example. And these new architectures would enable new applications. And for the purpose of this presentation, we are focusing on these abundant data applications that includes AI, that includes graph analytics, and so on and so forth, from the deeply embedded systems all the way to their cloud. Now, since I already talked about architectures, let's look at how is computing today. And in spite of 60 years of massive progress, computing today is pretty boring because you have this one-dimensional plane with some transistors on it. Yeah, you have some some wires going in the third dimension, but that's it. And then you have that memory chip that's like shown on the extreme right, top right of this slide. And as a result, you have to go back and forth between that compute chip and the memory chip, and there causes your memory wall, irrespective of whether you're von Neumann or not. So moving forward, what we need is the following. We need actually something, and this is where animation sometimes messes up on Zoom, so we will see what happens. So sure enough, it does mess up. So I will have to get out and get back to my next slide. This is typical problem with Zoom. So what you need is, think about, you know, we are going to fetch the miniaturization wall that we just talked about and the memory wall. Given that, we need layers of memory and layers of compute, number one, right? Because we have the miniaturization wall, we are not going to go beyond 0.5 nanometer maybe in the next 5 to 10 years. Now, when you have layers of memory and layers of compute, that seems like you're building a high rise. If you built a high rise, but you forgot to connect the various floors with many elevators, that's no good, which means that you need very dense interconnects, ultra dense 3D between the various layers of this memory and interconnect and logic. And you have to make sure that these layers of memory and layers of logic, they're at least as dense and they're at least as efficient as silicon technologies. So if we can satisfy these 3 points that I just talked about, then we are in a good shape, because we are overcoming the miniaturization wall. Because of the dense vertical interconnects, the ultra dense 3D, we are overcoming the memory wall, for example, or the connectivity wall. And then, of course, we want superior devices for memory and logic so that we overcome the power wall. And on top of that, you can always add functionality, for example, by using sensors. This is something that's very difficult, if not impossible, with business as usual. So this is our concept of what we call our next nanosystems. And a whole bunch of us, a few years back, we put together a position paper for this concept. And I would like to draw your attention to this very recent paper, this is called the LMC density metric that a bunch of us wrote together. This becomes very aligned with this next concept, because what this paper argues is that moving forward, this notion of nodes, node names, or node terminologies that we use, that should go out of the window, because now we have to think about a density metric for semiconductor technology in terms of what we call LMC, or logic, memory, and connectivity. And we express the density of logic, density of memory, and density of connectivity that goes hand in hand with that next concept that I was talking about on the earlier slide. Now, next is a concept, and there are many ways of implementing next. And for the rest of this presentation, I will focus on one specific way of implementing next, because that's something that we are building in an actual fab, where we have layers of computing logic that we are building using one-dimensional carbon nanotubes, although we also look at two-dimensional FETs. For memory, we look at MRAM and 3D resistive RAM, because they have complementary properties with respect to density, with respect to access times and energy, with respect to endurance and retention. But the really important points are, A, ultra dense fine-grained three-dimensional vias, no TSVs. B, it is fully silicon compatible. You can build this in a silicon foundry. And C, even though I show layers of thermal, for the first generation of our architecture, where the logic on the upper layers are used for memory accesses, you do not need special thermal solutions. In the next generation of our next architectures, where you need to put heavy duty compute on the upper layers, because you do not have, you have already hit the miniaturization wall by then, that's when new thermal solutions are essential for the upper layers. And this is the genesis for a major DARPA program. It is the 3D SoC program. It's at the scale of $100 million. I was told this is perhaps the biggest program that the DARPA has funded the academics for. And this is led by Max Schulaker, my former student. The key point over here is that Skywater Technology Foundry is a real silicon foundry where all these technologies are being implemented so that we actually have these technologies available for you folks to tape out. So I will very quickly go over a few points and wrap up my presentation. Some of you have already seen detailed aspects of some of these. Why are we focusing on carbon nanotubes for logic? That's because they provide 9x projected energy delay product benefits. This is collaborative work between Stanford, IMEC, and TSMC. And now there are actual demonstrations of carbon nanotube processors, the latest being a full RISC-V fully complementary carbon nanotube processor built by Max Schulaker of MIT. For memory, we are focusing on resistive RAM for various reasons. A, for its non-volatility, for the fact that they can store multiple bits per cell. We actually demonstrated the first multiple bits per cell resistive RAM-based system. Here, there is an animation thing over here, so you cannot actually see the multiple bits per cell over here. We have been able to show 10 years of continuous AGI in spite of endurance challenges with resistive RAM. But what is really exciting is by a combination of a concept called 1T NR resistive RAM and multiple bits per cell, we can achieve more than 100x on-chip memory versus what's available today or at the end of the roadmap. So just think about 100x more memory on your chip, talking about memory wall. And this has actually been demonstrated using the Skywater Technology Foundries and also in collaboration with CELAT in France. So those are the component technologies. And then we have 3D integration. Now, remember, what we want is very dense vertical connectivity, which is not given by TSVs, because TSVs are these big fat pillars that are connecting two layers. I liken them between the 4 bridges between San Francisco and Berkeley, and that's why you're always stuck driving between San Francisco and Berkeley. Instead, you want millions of bridges between San Francisco and Berkeley so that you are never stuck. The only way to have this very dense vertical connectivity, one highly promising way to do that is what is called monolithic 3D, where you use the existing interlayer vias that you use for metal interconnects. Now you use them for vertical interconnects. But for that, you need to be able to build things at a low temperature of less than 400 degrees C, and that is uniquely enabled by this carbon nanotubes and this resistive RAM. You can build them at a very low temperature. Are these just some fantasy land? No, we can actually build actual systems in an actual foundry. So in the lab, for a very long time, we actually built nano systems. We even built a hyperdimensional computing system, or HD, and Tayana is going to talk about HD in the next presentation. But now all these technologies are working in the actual silicon foundry, which is the Skywater Technology Foundry, the nanotubes, the resistive RAM, and the monolithic 3D, which creates exciting opportunities. I would end this presentation by making one more point, because I have 2 more minutes, which is that I could stop this presentation at this point and say my way or highway, right? You use these nanotubes, use this resistive RAM, and use this monolithic 3D, and you build this next chips. But remember, next is a concept. And I just showed you one implementation. And I know better that many of you have better ideas about device technologies, memory technologies, integration technologies, and so on. So as a result, Mohamed Sabri Ali, who was a former student of David, who is here, he actually built a next simulation framework where we can go all the way end to end between heterogeneous nanotechnologies, various concepts you might have, and the emerging set of applications, and try to understand where we might get a lot more benefits, a lot of benefits and alternative implementations. So when you actually use this framework, you can actually show that with the next implementations that I showed you, that you can achieve massive benefits. But not only that, you can explore between technology, architecture, and applications. For example, looking at the vertical connectivity, that when you have dense vertical connectivity, you get a lot of benefits. If you have TSVs, you may not get a lot of benefits, for example. So that is also possible. So I would like to thank the student sponsors and collaborators. And some of you that are, on this webinar, you can identify yourselves, on this slide. So thank you very much for, all your collaboration. So to end this presentation, nanosystems can be built today. And as I said, CNFET, RRAM, and monolithic 3D, that's working in an actual silicon foundry. So it's game on to the next era, and you can achieve massive benefits. One point that I did not mention because of lack of time, the benefits that I told you about, these 1000x scale benefits, they are achievable with existing software, which means now if you tune your software to these new architectures, you would be able to get a lot more benefits for a wide range of applications. So I think I just took 16 minutes. So thank you very much for your attention, and I'm happy to take questions.